Okay, I'm going to apply the arithmetic geometric mean inequality to prove the following result. A cubed over b plus b cubed over c plus c cubed over a greater than or equal to ab plus bc plus ca. I'm going to prove this. That's not right. Prove this. For A, B and C, no, they can't be equal to 0 because they're divided. These must be strictly equal to 0. I'm just going to spend a little bit of time thinking about this. The first thing to observe is it's got a nice symmetry between A and B and C. If you change the identities of these guys, if you permuted A, B and C around, you'd still get the same thing. Because it's symmetrical in the three quantities. But well, let's just apply. Let's just y plus z, we proved, was greater than or equal to 3 times x, y, z to the 1/3. So let's try that with x, y and z being these guys here. So the left hand side, which equals this guy here, a cubed over b plus b cubed over c plus c cubed over a, is greater than or equal to 3 times the cube root of the product. So that's a squared b squared c squared all to the power 1/3. So that says it's greater than or equal to 3 times a, b, c all to the power 2/3, which is great. That's a nice little result. That's a nice little result. It's quite a pleasing result. That's quite nice, but it's not really what we're after. It's not really what we're after because here the right hand side is a sum of things, and so it's not really very helpful. Let's just start again with that. We've got a cubed over b plus b cubed over c plus c cubed over a. Okay, what am I going to do with that? Well, I'm going to consider a cubed. I'm going to use this inequality here. X plus y plus z greater than or equal to x, y, z to the 1/3, and then there's 3 of those. I'm going to use that inequality, but with a cubed over b plus b cubed over c plus, and then what I'm going to do, plus something, and I'll fill that in a minute, is greater than or equal to 3 times the cube root of a cubed over b, b cubed over c times something. And what we want to do is to make that nice and symmetrical in some way. Oh, this is to the power 1/3. We want to make this nice and oops. I'm not sure what's happened there. Can I still draw? Yeah, back to square one here. Well, it's pretty clear. Well, what's in here? We've got an a cubed b squared over c. Well, the only thing that's really going to make any sense is if I put a bc in there. If I put a bc in there, then we'll get a cubed, b cubed, and the c will disappear. So I'm just going to put b and c in there on the grounds that on the right hand side we'll get something simple. And of course, what's going to happen? You can see this bc here kind of links in with that bc there, but that's not why I'm choosing that. I'm choosing that because I want to make this simple. I asked myself, here's a nice inequality with 3 variables in it, the 2 that I want and a kind of an odd one. Well, let's just see what happens. A cubed over b plus b cubed over c plus bc is greater than or equal to 3 times, well, we worked out the answer out already, haven't we? It's going to be ab. Ah, that looks quite nice. That looks quite nice. That's almost what we wanted. We've got a BC and an AB. But when we go back to the original question, the original statement, which is this one here, we've got this beautiful symmetry. I've just realised it's not invariant under any permutation of A and B and C. It's invariant under cyclic permutations. It's not. If you swap A and B, it's going to be different because you get this swapped over. But if A goes to B, B goes to C, and C goes back to A, if they go round in a circle, C back to that's okay. So it's got some forms of symmetry in here. So what I'm going to do is I'm going to use exactly the same thing again, but with A cubed over B plus, let's get this right, C cubed over, it's this one here, isn't it? C cubed over A. And then instead of BC, I'm going to have AC. And that's going to be greater than or equal to 3 times, and it's going to be the same line of logic here, AC. And of course I'm going to do the third one, B cubed over C plus C cubed over A plus what's left, it's going to be AB, isn't it? And that's going to be greater than or equal to 3 BC. Well, now I've done it. Now we can just add everything up on the left hand side and the right hand side. I can say that 3, no I can't, I can say that 2 A cubed over B plus B cubed over C plus C cubed over A. Why is it 2? It's because I've got 2 A cubes. I've got 2 A cubes over B, I've got 2 B cubes over C, and I've got 2 of these guys here. Plus AB plus AC plus BC from these guys here, greater than or equal to 3 AB plus BC plus AC. Okay, so that tells me that A cubed over B plus B cubed over C plus C cubed over A greater than or equal to 2, oh no, the 2's cancelled, I'm sorry. The 2 cancels. AB plus BC plus AC QED. Well, that's quite a nice little demonstration. That the hard thing, there's 2 hard steps here. You see, your first instinct is to try this 3-way arithmetic geometric inequality out, and it doesn't help. But you look at it and you try and make it help. You try and force it to work by sticking in some extra term for this second term here. You kind of break the symmetry between A and B and C simply by bunging in another term here that makes the inequality useful. And then you need to do it for the other 3 variables in turn, or the other 3 places in the formula in turn, and then you get your answer. I'm going to stop there. I think that's a nice little inequality, that. It's worth just spending a little bit of time asking what happens if A equals B equals C, strictly greater than or equal to 0. Well, that gives me A squared plus A squared plus A squared is greater than or equal to A squared plus A squared plus A squared. Oh, well, yeah, of course it is. I'm not sure what's happening there. Greater than or equal to, well, duh. Of course it is. We've got 3A squared. It's greater than or equal to 3A squared. And again, this is the hallmark of a good inequality, that when you shove simple values in, where they're all equal, they've got to be strictly greater than 0 because I'm dividing by them. When you bung equality in here, you get equality out of the relationship, which is quite nice. So I'm going to stop there.